So now we've studied the effect of thrust-to-weight ratio. Let's now look at the power consumption of each robot. So in this picture, I show you 6 different robots that we've built in our laboratory. Each one uses a different motor, has a different frame, and has a different payload. So because of that, the thrust-to-weight ratio is different, and the power consumed is also different. If you plot the power drawn as a function of thrust for a given robot, you'll find that the slope of this curve is roughly 200 watts per kilo. If you look at the power consumed and the power delivered by different types of batteries, you'll find the blue dots show the power consumption, which is around 200 watts a kilo, and thankfully the batteries produce more than 200 watts per kilo. So this gives you some idea of how to pick batteries so that you can actually support the power consumption for the motors and provide an extended life for the quadrotor. So when you think about system design, you have to think about battery selection, and when you think about battery selection, you have to think about the power consumption. In addition to power consumption, you also have to think about the total energy carried by the battery. In this plot, we show the specific power plotted against the specific energy for a variety of batteries. On the y-axis, you see watts per kilo. On the x-axis, you see watt-hours per kilo. You'll see that most lithium polymer batteries produce around 200 watt-hours per kilo. There's really nothing on the right side of this band. To contrast that with how humans perform, if you look at a piece of adipose tissue or fat, that carries about 10,000 watt-hours per kilo. This is several orders of magnitude more energy than is carried by batteries. If you look at the power consumption, robots consume about 200 watts per kilo to hover. If you look at humans, we consume a lot less than that to walk around or even to run. In fact, if you look at the fastest man on Earth, Usain Bolt, he's estimated to consume about 20 watts per kilo. So our robots are 10 times more inefficient than possibly the most inefficient man on Earth as he runs the 100 meters race in 10 seconds. Even if you look at bicyclists like Lance Armstrong, he consumes about 6 watts per kilo. So the moral of the story is, our robots are inefficient. Actually, hovering is an inefficient mechanism. So we need lots of power to power our robots. And if you look at lithium polymer batteries, which represent the best choice of batteries today, they don't carry a lot of energy. So what do we do when we need a lot of power and we don't have batteries that carry a lot of energy? Well, we can try to reduce our weight and go on a diet. And that's what we try to do in the lab. We try to build smaller and lighter quadrotors. If you look at the mass distribution in a quadrotor and look at different components, how they contribute to the total mass, you'll see a lot of variability. You'll see that the batteries contribute about 33% of the total mass, and the motors plus propellers contribute about 25% of the total mass. Of course, if you add sensors like laser scanners and cameras, that increases the total mass also. If you take a laser scanner with a range of about 30 meters, it consumes about 10 watts for operation, but because it weighs 270 grams, it consumes another 50 to 60 watts for mobility. Here's a camera system that weighs about 80 grams. It costs us 1.5 watts to operate this camera, plus an additional 15 watts for mobility. So when thinking about the payload, we want to also think about the power consumed in addition to the thrust-to-weight ratio.